Hello, everyone. Good afternoon. This is the lecture for Math 100 for the 9th of December. We are now officially 26 days until Christmas, one of my favorite times of the year. Not really, I hate Christmas. But more importantly, only a few more days until you actually get your break. So I hope you're all excited for that. And well, let's get right into this subject. So we're going to talk about light today in physics. Right? Obviously something I'm not too familiar with because I'm pretty heavy. That's a joke. Light, heavy, funny. I know, Mr. McKeever is hilarious. So we're going to talk about a couple things. We're going to talk about waveform today, frequency, interference, speed of light, electromagnetic spectrum, light transmission, how we perceive light, and then some physical therapy applications, right? So just a little bit of light humor before we start here. Where does bad light go to be punished? The prism. What is a light year? A year with 1/3 less calories than the previous year. What's the easiest way to observe Doppler effect? Stand outside at night and look at the cars. The ones approaching you are white, while those moving away from you are red. We talked about that. If you don't get that, you have to look that one up. Does light have mass? There's no definitive scientific proof to say that light is Catholic, so obviously it cannot have mass. And then finally, Photon checks into a hotel and the bellhop asks if he needs assistance with his baggage. Photon looks at the bellhop and says, "No, I'm traveling light." All right, that's my Jimmy Kimmel for the day. So we're going to talk about waveforms to start with, right? So waveforms are typically looked at in form on a wavelength, right? How the wave looks. And most of the times when we deal with this, we talk about a sinus curve or a sine curve. It's a pictorial representation of what a wave looks like in simple harmonic motion. Oppenheimer first demonstrated that a pendulum swinging back and forth traces out a straight line over a stationary surface. So as it swings back and forth like that, right? So as the pendulum just kind of swings back and forth, it makes a straight line this way. But if you put a paper under it and you have a pen on that pendulum, it traces a wave. Right? And so that became the first kind of example of what waveforms look like. So the high points in the waves are called the crests. The low points are called the troughs, right? Amplitude determines the distance from the midpoint to the crest or trough of the wave. So either from the midpoint of the wave to the top, from here to here, or from the midpoint to the bottom. That's the amplitude of the wave. The amplitude is the maximum displacement from equilibrium, equilibrium being base status, right? So the wavelength is the distance from one top of a crest to one top of another, right? Could also be equidistance between successful identical parts. So we could say from the top to the top, from the mid to the mid, from the trough to the trough. It really doesn't matter where we define that, as long as those points are identical in two different points of the wave. Right? So when we think of like wavelengths at the beach, they're measured in meters, ripples in a pond in centimeters. In light, it's literally a billionth of a meter is how wavelength is measured. So it's very, very small wavelengths. That coincides with frequency, right? So wavelength being the distance between 2 points on it, right? Frequency is how often something goes by. It's the number of back and forth vibrations, usually in a second. There's a clear distinction here between frequency and speed. Right? Frequency is very different. Frequency is how often something occurs. Speed is how fast it occurs. How fast does that wave get from point A to point B? That complete back and forth vibration is one cycle. If a vibration occurs in 1 second, the frequency is said to be 1 cycle per second. If it's 2 vibrations in 1 second, it'd be 2 cycles per second, right? The frequency of the vibrating source and the frequency of the wave produced are often the same. So the frequency unit we deal with in physical therapy and science and everything is usually called the hertz, right? And sometimes learning this really hurts. It's a frequency of 1 cycle per second, otherwise known as 1 hertz. 2 cycles per second, 2 hertz. 3 cycles per second, 3 hertz. 300 cycles per second, 300 hertz, right? The higher the frequency, we often adjust it to start adding those prefixes to it, right? Kilohertz, megahertz, gigahertz. We're starting to get in the gigahertz bandwidth now with a lot of our Wi-Fi devices, right? So that means literally billions of cycles per second, right? So you've got a 5 gigahertz band router. We talked about this back in sound, right? If you got a 5 gig band router, that's saying that every second, right, that wave is cycling 5 billion times a second. That's a lot of cycles, in my opinion, right? Almost all information that we receive from the world gets to us in the form of wave, right? Sound energy, it's a wave. Light energy that comes in our eyes, it's a wave, right? Radio and television sets, waves. Even the signal that comes through your cable, right, is a wave on the electromagnetic spectrum, especially if you've got something like the new forms of cable where it's fiber to curb. You may have heard that, FTC, your cable company, especially if you're at Cox in this area, they're actually really working hard on getting what's called FTC, fiber to curb. What that means is instead of having traditional copper wires running your cabling, it's now fiber optic cables. Great news. That means 4K signal, beautiful picture, stuff like that. Bad news is it means the cables are really easy to damage too, which means they have to come out and replace them frequently because, you know, animals and, well, whoever else messes with it. In my neighborhood, it could be homeless people because they stole all the copper out of one of the cable boxes here once. But that's beside the point. You can calculate the speed of a wave by multiplying the wavelength by the frequency, right? The speed of a wave depends on the medium through which it's traveling. We talked about that with sound, right? Sound waves travel at different frequencies based upon the medium it's traveling through. And remember, whenever we say medium, we're not talking about a person that speaks to ghosts. We're talking about what it's traveling through. As I throw this ball back and forth, the medium it's traveling through is air. If it was traveling through water, I'd be having a really bad day, right? If it was traveling through lava, it'd be even worse. So the speed of a wave is calculated by multiplying the wavelength by the frequency. So how long those waves are by how frequently they occur. If the wavelength is 1 meter and 1 wavelength per second passes the pole, the speed of the wave is 1 meter per second. If the wavelength is 3 meters and 2 crests pass a stationary point per second, then 3 meters times 2 waves pass in 1 second. Therefore, the speed is 6 meters per second. The formula for this, right, is as shown there. V equals, I think that's lambda. Don't quote me on that. My brain just completely, that's why I was like, it's right there. And my brain just completely shot out on that. That was fantastic right in the middle of the lecture, right? The main thing here is we have V representing the wave speed, right? Our good old Greek letter representing wavelength, and F is the frequency. So velocity is important. And remember, we could also just substitute an S in there for speed, but we usually don't use S. V means velocity, meaning that it has a direction, it's going somewhere. As I am speaking right now, my voice has a velocity. It is traveling from my mouth to the microphone. It is getting picked up by the microphone. Interestingly enough, the microphone is converting that into an electric signal, which is still a wavelength, sending it through my USB cable. That USB cable goes behind my desk and goes over into my computer that's over here. My computer then captures that and records it in a digital format. That way, while you guys are listening to it, it gets decoded, right? Sent back through a cable somewhere in your house, maybe, or maybe just on your laptop, however you have it set up, and gets played through speakers. Those speakers create vibration. Those waves travel through the air, and they come into your ear. How many of you guys have heard yourself speak on a recording and are like, oh my God, right? I listen to my lectures, and I don't know how you guys do it. My voice is the most obnoxious voice I think I've heard. And it's usually the way people think about their own voices, right? I need to get Matthew McConaughey to record my lectures or something. All right. Or somebody said once that I sound like Joe Rogan, which I think is utterly hilarious. Hey, Jamie, look that up over there. Anyway, moving on. We talked briefly about interference in the sound lecture, right? We talked about how interference can affect your overall audio quality and how you hear things. We also talked about how certain car manufacturers and headphones, right, are using interference to help block out sound. Remember that constructive interference is where things increase in amplitude. Destructive interference is where it either reduces the amplitude or cancels it all out, right? So in the case of waveforms, when you have constructive interference, When two waves come along and they're in sync, so you have one wave that's coming along like this, right? And you have another wave that is in sync with it, right? So it's coming right along with it. It's moving perfectly in sync. The resultant wave will have an increased amplitude because those two waves are going to combine together. It was a really bad drawing on Mr. McKeever's point, but I hope you get the idea, right? So when you have constructive interference, it increases the amplitude, increases the height of those waves, right? That's different than destructive interference. So here we have that one wave again. That was a really bad last wave, but oh well, we'll get through it. When you have destructive interference, a couple things can happen here. Let's just say these waves are perfectly out of sync. So that means the waves match each other in height, as much as Mr. McKeever can draw this. And they match each other in form. Oh, that one's gonna be a big one. So what's gonna happen when they match each other out? Well, those both are gonna cancel each other out and you're gonna get a flat waveform because they're gonna cancel each other out, right? Whereas let's say we do something a little different here. So now we've got a wave. Do I have a waveform drawing tool? Let's see if this is waveform drawing tool. Well, that's a lot thicker. Never mind. I don't want that one. Back to my original one. So let's say we've got a wave that's going like this. Right, so we've got a beautiful wave going on here. And then we got another wave that comes in. It's still out of sync with it, but the hills aren't as big. So it's opposite in sync, but the hills aren't as big. What that's then going to do is it's going to create a smaller wave. So it's going to figure out which one of these is the stronger. The green wave is stronger, so it's going to keep that green wave form, but instead it's going to be a smaller wave, right? So what could that equal, right? We talked about with sound waves, that could equal that in an area where the sound is really hard to hear. Or, you know, if it's equal and opposite, then it'll cancel it out and you have a dead spot. Light can be the same way, right? We're going to talk about different ways to polarize and block out light. So light, almost everything we see is made by visible light that it reflects, right? Some materials such as air, water, or window glass allow light to pass through and are transparent. Other materials such as paper or frosted glass allow the passage of light in partial portions, so we can see some of it through, right? That may be translucent. And then we may have some that just block light altogether that are opaque. We know now that scientists have agreed that light has a dual nature. It's part particle, meaning there's particles flying off in it, and it's part wave, which we've already discussed. Light travels about 1 million times faster than sound in most mediums. That means if you travel light through metal, it's really fast. The speed of light is about 300,000 kilometers per second. Think about that for a second, because if, let's say you're doing 100 kilometers per hour, that seems fast in a car. Right? I think it's about 65 miles an hour, if I'm correct, right? We're talking 300,000 kilometers per second. This is the conundrum when talking about traveling light. Because if we can reach that light speed there's going to be a lot of G-force on us. And we're going to be pulling some G's back here. The speed of light in a vacuum is a universal constant, right? We usually call it c. Light is so fast that even if a beam of light could travel around the Earth, it would make 7.5 trips in 1 second. Think about that. Hoo-wee. Could we change travel if we could transport people at the speed of light? I mean, instantaneous travel, basically. Especially if you could get one light beam can make it around the Earth in 7.5 times in 1 second. It's amazing. Light takes 8 minutes to travel from the sun to Earth. And then 4 years from the next nearest star, so Alpha Centauri, right? The distance light travels in 1 year is called a light year. So when we're talking about measuring distances to other stars, right, we talk about it in the terms of light years. How long does it take to travel in 1 year? So we know that light to Alpha Centauri takes 4 years to get there. That means The distance from here to Alpha Centauri is 4 light years away. Think about that for a second. If the speed of light is traveling at 300,000 kilometers per second, right? So 300,000 kilometers per second, how many miles would that travel, or how many in a day? Let's see. So 300,000, let's see. So seconds, how many seconds in a day? So 60 seconds in a minute, right? Times 60 minutes in an hour, times 24 hours. So we have 86,400 seconds in a day. Times that by 300,000. And you're now talking 2 to the exponent of 10, 2.5 to the exponent of 10 times 10 to the 10th, or 25 billion kilometers every day. Think about that. That's fast. 25 billion kilometers a day. Good grief. So think about that times a year then, right? Because that's per day. So we'll times that by 365. We're now talking, I don't even know what number that is. I think it's a quadrillion. So 9 quadrillion miles in a year. It's insane. So in a vacuum, again, the speed of light is a constant 300,000 kilometers per second, right? We call this the speed of light c, right? You often heard Einstein's equation, E equals mc squared, right? Energy equals the mass times speed of light. Light travels slightly less in the atmosphere, but speed usually is rounded to c. So maybe in the atmosphere, I travel a little slower, but we just kind of round it to that area. In water, light travels at about 75% of its speed in a vacuum, so about 0.75 c. In glass, 0.67. So glass is going to reduce its speed. In a diamond, which is why diamonds sparkle so much, it costs only about, or travels only about, it costs a lot. Diamonds cost a lot, you see, right? It only travels at about 0.4 carats. I'm joking, 0.4 times the speed of light, right? When light emerges into the air from those objects, it then it picks up speed back up to c. So we can slow it down with objects, but it eventually just picks right back up to its normal speed. So all light falls on the electromagnetic spectrum, right? The electromagnetic spectrum consists of radio waves, microwaves, infrared waves, light, ultraviolet, ray, X-rays, gamma rays, right? That's how we create the Hulk, the gamma rays. Light is energy that is emitted by accelerating electric charges, often electrons, to create photons. We'll talk a little bit about that. We're going to gloss over that part of it. This energy travels in a wave that is partly electric and partly magnetic. So that's why it's called an electromagnetic wave. Light is a portion of the family of the electromagnetic waves that includes radio, microwave, X-rays, blah, 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 blah. The range of electromagnetic waves is often called the electromagnetic spectrum, right? So here we have kind of the electromagnetic spectrum. We have radio waves out here in 10 to the 4th and 10 to the 6th. And then as we get closer and closer and closer, we can see that light itself is really only a small spectrum of our vision, or of the electromagnetic spectrum, right? It's a really tiny area. And that's kind of the bottom description kind of shows how we have a magnetic field versus an electric field in the direction. So it shows that it is both electric and magnetic. So that means technically it has inertia. The lowest frequency of light that we can physically see is red, right? The highest visible light, violet, has nearly twice the frequency of red light, right? So electromagnetic waves with frequencies lower than red of visible light are called infrared. So anything below red, infrared. So such as like the heat lamps at your local fast food restaurant, right? Those are usually infrared light. You can't see the light coming off them, but it is light and it keeps your French fries warm, right? Higher than those of violet are called ultraviolet or UV rays, right? They're responsible for our sunburns. They're also responsible, we're going to talk about, for using wound care and sanitization. So what happens when light strikes a medium, right? So I've got my little Coke bottle here. Why is it through some of this Coke bottle up here, light travels through fine, but it gets down here to the Coke and it kind of changes color? Well, that depends upon how light is passing through those materials and what the atoms do to absorb some of that energy and then readmit it, right? Light is carried in an electromagnetic wave generated by vibrating electric charge pulses. When light strikes a matter, so when light's striking me right now, the electrons in me are forced into vibration. And then exactly how a material responds to that light depends upon the frequency of light and the natural frequency of electrons in the material, right? Visible light vibrates at a very, very high rate, more than 100 trillion times per second, right? That's just insane. And that should be 10 to the 14th hertz, not 1014. I'll fix that. To respond to these ultra-fast vibration, the particle must have a little inertia, right? Electrons with their small mass can vibrate this fast without even causing problems. So if we have something that transmits light and allows things to pass through, like a window, they are considered transparent. They allow light to pass through. Glass and water are excellent examples of transparent. Water for the most part, right? Now, if we're talking like water in some scummy ponds, maybe not as transparent as maybe something like the ocean down in Aruba, right? I was always terrified. There's funny stories. I was terrified because I used to go to the beach, and we used to go to either Rehoboth Beach, Ocean City, Maryland, or to Jersey City Beach. And I was terrified to get in the water because, man, you couldn't see anything in the ocean in those areas. It was just kind of murky. And the first time I went to the Bahamas and I saw that, like, literally 40 yards out from the beach, you can still see all the way to the bottom, I was just in amazement, right? So that tells you that what's in that material can affect its transparency, right? We obviously have some pollution towards our shores. Materials that are springy and elastic respond to more vibrations than others, right? The natural vibration frequencies in an electron determines on how it's strongly attached to the nearby nucleus, right? We talked about this briefly with natural vibration. Glass itself is transported to all the frequencies of the visible light, right? So it allows kind of all those frequencies to pass through. Glass is an interesting substance, really, because there's a lot of scientific discussion of whether it's a very, very fast moving solid or it's a very, very slow moving liquid. Because glass eventually, as time goes, runs. It changes the way it looks. That's why if you look at sort of an old window in an old house, it's not as clear as a newer window, right? And it's not from scratches and stuff like that. The glass kind of gets runs in it. The frequency of the re-emitted light is identical, right? Because what happens, the light strikes the glass, causes excitation, gets through, it slows down as it passes through glass, and as soon as it gets the other side, it speeds up again, right? The main difference is a slight time delay between absorption and readmission. Time delay is really not that much, right? Results in a lower average of speed traveling through the material, but once it gets through the material, it's back up to its C. Infrared waves with frequencies lower than visible light, not only the electrons, but also the entire structure of the glass, right, will pass through, cause vibrations, right? The vibration of the structure increases the internal energy of the glass and makes it warmer. Glass is transparent to visible light, but not to UV and infrared lights, right? So on the case that here we have a flower pot down here, right? We have some light going through, but this glass particularly is helping to block out ultraviolet and helping to block out infrared. Certain different forms of glass, like those in greenhouses, may allow more of that infrared or that ultraviolet light through, depending upon what you're going for, right? Grow lights for plants, right? I hear that you use them to grow pretty flowers and stuff like that. That's what I hear here in Las Vegas. Grow lights allow for that light that doesn't normally pass through in order to cause the plant to grow at a higher rate. Opaque materials, right? Any coordinated vibration given by light to the atom's molecules are turned into random kinetic energy, that is, into internal energy. So when you have an opaque material, such as the back of my phone here, right? If light is coming through and striking the backside of my phone, I don't see the light coming out this side. Well, why is that, right? And if I put this up against the camera, all of a sudden, right, if I push it all the way up against, all of a sudden, all the light from my light over here is blocked. It is opaqued. It is blocked. Well, what's happening is the light from this light is hitting this and causing vibrations, and it's absorbing it into internal energy. Now, if it absorbs enough of it, it can heat it up, right? Set this black phone outside on the pavement for a little while in the summer, and it's going to get really warm. A lot of materials that absorb light without readmission and thus allow no light are called opaque, right? Wood, stone, people, we are opaque. If you could see through us, that'd be really creepy, right? You'd be an invisible man. Theoretically, you could do all kinds of creepy things if you could see through you. But even in, you see those Invisible Man shows, or like in the comic books, Invisible Woman from Fantastic Four. And I play Destiny a lot, right? And in Destiny, the Hunter class has invisibility. The one thing I like about science fiction and even games like that is they still show that even if you are invisible, you are still partially sight. You can see things because it's going to distort the light around you. So invisibility is never going to be perfect, right? The cloak from Harry Potter, excellent example, or partial excellent example. Sometimes that made them too invisible, right? But even if you had something that would bend the light that way, you would still be partially visible. There's all kinds of new technology that's coming out right now from the military that are invisibility cloaks, right? That are going to allow, instead of, it's not going to allow light to just pass through it. What it's going to do is it's going to take pictures basically of its surrounding and project them around the object. So it looks like that object's not there. It's not truly invisible at that point. It's camouflaged. Stealth planes are excellent examples of things that use materials to change the way their radar reflection comes back at them, right? Radar is on the radio frequency. When you use radar, what you're doing is send out a waveform. Yeah, if I was using radar on my microphone right now, it'd send out a waveform, it'd bounce off the microphone and return back to my receiver, and it would show me the general shape of the microphone. And based upon that general shape, I could determine it's a microphone. Stealth planes are designed with specific materials and also specific shapes and stuff like that, right? The stealth planes look kind of weird, that allow those radar waves to hit them and kind of reflect off and continue off into space. Or that it only sends back such a small signature that the plane itself looks like a small bird, right? It's actually pretty neat technology. In opaque materials, any vibration from light are turned into random kinetic energy, that is, again, internal energy, and the material becomes slightly warmer. Even just sitting here, right? You're going to get a little bit warm from light. It's just the way it is. Metals, also opaque, right? In metals, it's neat. The outer electrons of the atoms are not bound to any particular atom. When the light shines in the metal, it sets them free into vibration. Their energy does not spring from atom to atom, right? It's remitted as visible light. And it's a reflection. This is why metals themselves are shiny, right? You get a nice copper plate or a nice gold sheen to it, right? Here we go. Pair of scissors, right? If I move them around, you can see the shine on them. The light's hitting it, exciting it, and it's bouncing back off and showing as a pretty kind of reflection, right? That's why we can use that to see ourselves, right? When we need to mirror, we go to a piece of metal that actually reflects our image. It's actually pretty cool the way it works. Our atmosphere itself is transparent to visible light and some infrared, but almost opaque to high frequency UV rays. That's a good thing, right? There is some UV that gets through, but it's on the kind of lower end spectrum of the UV light. Clouds are semi-transparent to UV, so you still can get a sunburn even on a cloudy day, right? UV also has a high refraction rate and reflection rate. So that means even if you're sitting under an umbrella, that can bounce off the sand and water and still give you a sunburn, even if you're hiding from the UV, right? Which is why it's really important that if you are going out, to protect your skin with sunblock. What does sunblock do? Sunblock gets absorbed into your skin and creates an invisible barrier that helps block most of the UV rays, right? That's where it's talking about SPF. The higher the SPF, the greater the blocking of UV rays. You can go all the way, I think I've seen SPF 120 now, and it's going to block most of the UV rays that are going to get through. This is the concern for us in the environment, because if you remember a few years ago, we were talking about the hole in the ozone layer, right? And ozone is really, really responsible up in the upper atmosphere for blocking those UV rays. If we have a hole in the ozone, all those UV rays are now going to escape and get through. And I don't know if any of you have ever watched, there was which movie was it? I think it was The Day After Tomorrow. I can't remember if it was that one, or no, it was the one with Gerard Butler. I can't think of it. Geostorm it was called. Really bad movie, but it's fantastically bad. So must watch it if you can get a chance. They figure out a way to manipulate the environment. Well, one of the problems they release is they actually allow extra UV rays to come through the air. And when it does, it literally crisps people. And that could be a real thing if we lose our ozone protector, right? Now we talk a lot about global warming, climate change, right? That's part of what this is. This is the UV rays coming down and heating up our planet. But even more important to that is, as we lose more and more of our atmosphere due to these greenhouse gases, we're going to sunburn more. And our skin is not designed to handle that. I mean, we can resist it somewhat. Some people have a higher resistance to sunburn. Some people just get burnt by thinking about the sun, right? But in general, our skin is not designed to handle, high volume UV rays. So if we get problems with our actual ozone layer and it starts depleting, we're going to experience more and more sunburns. It's going to get worse and worse, right? So this is why it's kind of interesting the way those UV rays pass through. Visible light comes through for the most part, some infrared, which is why we warm up, but UV rays themselves are typically mostly blocked by our upper atmosphere. So let's talk about Punxsutawney Phil. Right? Now I successfully confused you about the topic. We're going to talk about shadows, right? So Punxsutawney Phil, if you're not familiar, this is a little groundhog in Pennsylvania who comes out every year. And if he sees the shadow, we get 2 more weeks of winter, right? Punxsutawney Phil comes out on, guess what? Groundhog Day, because he's a groundhog. That was the great Bill Murray movie, by the way, as well. But we're going to talk about shadows. That's why I use Punxsutawney Phil as an example, right? When we have a thin beam of light, it's often called a ray. So any beam of light, no matter how wide, can be thought as making a bundle of rays. A shadow is formed where light rays cannot reach, right? So if I hold up my hand here, the light's coming from this side, striking the back of my hand. Over on this hand, I've got a shadow. If I move my hand, this hand lights up, right? You can see it, right? It's lit up. Now I cover it, it partially blocks it. I can do the same thing with the camera and it'll change the focus, right? As I block the thing, it changes my focus because it's detecting the light coming in. I'm creating a shadow. Shadows formed where light rays cannot reach. We all have our shadow. Our shadow is our best friend. It goes with us everywhere, right? Sharp shadows are produced by small light sources nearby or by larger sources farther away. However, most shadows are somewhat blurry, right? Dark part on the inside, lighter part around the edges. And it's not a perfect representation of us, right? If it was, that'd be really creepy. A total shadow is called an umbra. Partial shadow is called a penumbra. Penumbra appears where some of the light is blocked while other light fills in. So you get kind of that mixed effect of shadow and light. Penumbra also occurs when the moon passes between the Earth and the sun during a solar eclipse, right? You have some of the light going around the moon, but you have this area where it's partially blocked. The moon's shadow barely reaches Earth, right? But if you stand in an umbra shadow, you experience brief darkness during the day. If you stand in the penumbra, you experience partial eclipse. The sunlight is dim, but the sun appears as a crescent around the moon. The Earth, like most objects in sunlight, casts a shadow, right? The shadow can extend into space, and sometimes the moon passes into it. And that's when we end up with lunar eclipses, right? Or partial blockage of the moon. And it can be seen by all observers in the nighttime half of the Earth, right? So as we turn and rotate, your shadow can actually block out the moon. That's how we get the different shapes of the moon. That's the Earth's shadow being broadcast on that moon, right? We get waxing crescents, waning crescents, all that fun stuff, right? And it tells you, if you looked at astrology, when the moon's in certain phases, people are weird. No, actually, I will say there's some sort of weird correlation that when there's a full moon that, those people with issues tend to be out more frequently. I don't know what that is. I don't think that's actually having anything to do with the moon. I just think it's because it's brighter, but whatever, I know. Polarization. As light travels in waves, right? The fact is the waves are transverse and not longitudinal. This is determined by the phenomenon polarization, right? If you shake the end of a horizontal rope, transverse wave travels along the rope. The vibrations are back and forth in one direction. That means that wave is polarized. It means it's going in one direction. So if I do it this way, the waves are traveling this way. If I go up and down, the waves are traveling up and down. It's not like they mix. It's not like they're kind of doing a circle. Vibrations back and forth in one direction are polarized waves, right? An incandescent candle or incandescent or fluorescent lamp, a candle flame, or sun all emit light that is not polarized, right? It's bright white. The electrons that produce the light vibrate in random directions. So when light shines on a polarizing filter, the light that's transmitted through is polarized. My glasses have a polarization to them, right? They have a polarization to blue light. So we can add a filter down the polarization axis that stops some of the polarized light from coming through. You can also use two polarized filters themselves that are exact opposites of each other and make a completely opaque block of light. This happened once to me. I have a pair of Oakleys that I wear when I need to block the sunlight, and my Oakleys are polarized, right? One of the neat things about polarized lenses are if you go like a creek or a waterway or something like that, you look down in, you can usually see clearer into the water because it's taking away the reflection. And a lot of fishermen and stuff like that like polarized sunglasses for going out and fishing with. But I got in my buddy's car, and my buddy had used polarized tint on his windows, right? So he's blocking part of the light coming into his car, which was really cool because it did keep the car cooler. But the funny part was when I turned my head and I had my head at a very specific angle looking out his window, excuse me, the two polarizations were exactly an opposite, and it made his window black. There was no seeing out through it. It was actually kind of neat. It was a true show of polarization, right? We can think about this kind of like skipping flat stones across the surface of the pond, right? Stones with flat surfaces parallel to the water bounce and they reflect. Stones with the flat sides at right angles to the surface penetrate. So if you throw like a ninja star, it's going to go down into the water. Light behaves similarly. The flat side of the stone is like the plane of vibration of polarized light. So we can use polarization to block out some light. Light reflecting from non-metallic surfaces such as glass or water vibrates mainly in the plane of the reflecting surface. So we can actually use that to our advantage and create things like polarized lenses to block specific lights. Some of your really high-end digital SLRs have polarized filters that you can put on them. If you're going out in bright sunlight to take photos, you can put a polarizing filter on to reduce the ambient light so the person looks more natural and less washed out, right? Even some of the phones have some polarization filters on them. I was looking, even Zoom has some polarization filters that I can do, right? That allow me to actually change the way I look. I'm not going to do it right now because I can't remember where those were. But they do allow polarization, right? So it allows for things to do things. Let's see. Well, actually, no, I can find it. Here it is, right? So I can change my polarization, and now I look different. What it's done is it's digitally done it, right? It's digitally now changed the absorption of the light around me, right? That's how we can get some cool tones like, where is it? Out here, we can get that cool sepia tone, right? So that's an effect of polarization is really what it is. It's changing the way the light's getting absorbed or bounced. But the main thing with us is we talk about colors when we're talking about our perception of light, right? Color is in the eye of the beholder, and it's provoked by the frequency of light emitted or reflected by all things. We see red in a rose when a light of certain frequencies reaches our eyes. Many organisms, including us, right, have defective color and may not see red in a rose, right? Some of us have color blindness, and we may not be able to see certain colors. If we pass a narrow beam of sunlight through a triangular shaped glass prism, Newton showed that sunlight is composed of a mixture of all the colors of the rainbow and can break it apart. Newton called this spread a spectrum and noted the colors were formed in the order of red, orange, yellow, green, blue. It's also indigo and violet, right? Regi Biv we learned in probably elementary school. And if we're below red, we're infrared. If we're above violet, we're ultraviolet. But we know that light passes through that. Sunlight is an example of what we call white light. White light is a combination of all the colors, right? And you can actually, if you're a real geek about this, and you want to be a real geek, and if you've read any of the Lord of the Rings series, the wizards, there are many wizards in the Lord of the Rings series, and they're named after specific colors of light, right? The ultimate wizard that you can be is the white wizard. The white wizard is the combination of all wizards combined, right? Saruman hoped to be the white wizard. He wasn't. It's chosen by the gods in that world. But anyway, that goes way too far into it, right? But the white wizard is supposed to have all of the powers of all the wizard's colors combined. Eventually, Gandalf comes back as the white wizard. He was the gray wizard, right? So Tolkien himself took a kind of a play on the way light spectrum works and created his mythology of how wizards are in that. It's actually kind of ingenious, honestly. Under white light, objects appear in red, or appear white, and colored objects appear in their individual colors, right? Newton showed that the colors in the spectrum were a property not of the prism, but of the white light itself. So when he split apart those colors, it was actually all of white. He was able to recombine the colors with the second prism to produce white light again. So he was able to take one prism here, one prism here. As it passed through the prism, it spread out into that visible spectrum and struck the other prism, which was combined back to white light. So that means all the colors atop each other combine to produce white light. So white is not a color itself, but it's all colors. Now, what happens if you break out your Crayola crayon box and you mix all the colors together? It doesn't happen, right? You'll say, oh, I got black. Well, there's a reason for that, right? But white is truly, that's because of the material the crayons are made out of. Light itself, white light is a combination of all colors. So my light bulb that I have in my top light lamp here has a yellow tint to it. It gives me kind of a washed out color. The light that I use for reading is a pure white light, right? That pure white light is a combination of all colors of the visual spectrum. Black, similarly, is not a color, but the absence of light. Objects appear black when they absorb light of all visible frequencies. Even a polished surface may look black under some circumstances. The ocean can look black with the lack of light, right? Highly polished razor blades stacked together and viewed on end appear to be black. If you look at, one of those really fancy Gillette multiple blade razors, sometimes if you turn them a specific way, the blades look black. Light that gets between the closest spaced edges of the blades gets trapped and is absorbed after being reflected many times. Black objects you see do not absorb all light that falls in them because there's always some reflection of it, right? So what it's saying is my phone has got a black case on it. It's not that it's an absence of light, right? But it's absorbing all of my light and reflected. You can see that up here, my phone itself is red because that's what it's kind of giving back. So the colors of most objects are due to the way that objects reflect light. The colors of an opaque object is the color of the light that it reflects back, right? So again, my phone has that little red tint to it because it reflects back the red tint. My little ball here that I keep messing with because I fidget too much is green, right? Light reflects objects the way light reflecting from object, like the way they sound, reflects from a tuning fork when set into vibration. So when that light strikes my ball here, it sets the molecules into excitation, and those exciting colors that bounce back are the colors I see. Different materials have different natural frequencies for absorbing and emitting light and radiation. At the resonant frequencies where the amplitude oscillation are large, light is going to be absorbed. The frequencies below and above the resonant frequencies, light will be re-emitted, and it'll be shown as a color. The color of an object, though, does depend upon the light used. Candle flame is deficient in higher frequency and emits a yellowish light. So things look kind of yellowish in candlelight, or in my cheapy light bulb that I have up there. Like, that is really a cheap light bulb, guys, just to let you know. An incandescent lamp emits all of the visible frequencies, but is richer towards the low frequency, enhancing the reds. A fluorescent lamp is richer in the high frequencies, so blues are enhanced, right? I can do that again with those filters, where I can go in here and I can choose my video filter, and I think I can enhance, there we go. I can enhance some of the fluorescence with it and causes my blues to become a little bit richer. So all of that can come into play when you're talking about reflection of color. The color of transparent object is the color of the light it transmits. So if I have a clear object and I have a blue light going through it, well, blue is what it's going to show, right? It's going to transmit the color of the light that it's transmitting. Blue glass, on the other hand, only transmits the energy of blue light, right? So if I have blue glass, it's going to only transmit the blue light. My glasses are blue blocking glasses. So when I look through them, if I take them off right now, my screen looks, well, I think I have a screen. Not sure. I don't have contacts right now. But when I put them on, my screen changes color. Well, why does it change color? Well, what it's doing is blocking some of that blue light emitting from my screen. It's when there are studies that have shown that that blue light is really kind of bad for our eyes. We still don't know the full effects of what's going to happen to us from years and years of blue light emission, right? But why would that maybe be bad? Well, what if I'm designing part of my game and I'm making the area very vibrant with colors? I might need a different pair of glasses that don't block blue light. And I don't think you can see it, but they're scratched the heck too, but that's beside the point. So the material in the glass selectively absorbs color light. It's called a pigment. So my lenses have a specific pigment to them. Usually, if you're looking at blue light colored lenses, they usually have kind of a yellowy tint to them, right? The electrons in the pigment atom selectively absorb specific frequencies in the illuminating light. Other frequencies are re-emitted, so it allows, again, my glasses allow most of the light through, but blocks a good chunk of the blue light. Ordinary window glass is colorless because it allows all frequencies through, right? But could we change that, right? We could put specific kinds of glass up that the only thing it allows is blue, or it only allows red, or only allows orange. That would be where you get stained glass from, right? It allows certain specific parts of the spectrum to go through. Sunlight itself is a composite of all the visible frequencies, right? The brightness of solar frequencies is uneven though. The lowest frequencies of sunlight in the red region are not as bright as those in the middle yellow and green region. Humans themselves have evolved in the presence of sunlight and were most sensitive to yellow-green. The blue portion of sunlight is not as bright and the violet portion is even less bright. So as we get up towards that ultraviolet range, and obviously we see less and less. So here's kind of a picture, visual frequency or visual thing of the visible light. And remember, on the electromagnetic spectrum, that visible light's only this little chunk, right? But what it shows you here is down here, right? So let me get my little drawer out here, right? Down here, we have our infrared portion. Over here, we have our ultraviolet portion. But this shows in the amount of process, the majority of what we see is in this portion right here. It's in that green, yellow, kind of orangey phase, right? So if we look up at the sun right now, the sun's going to look kind of yellow-orange. It's pretty cool the way it works. We look at the moon sometimes. The moon can kind of look bluish, right? And get a blue moon effect. That's because we see more in those specific frequencies. But although every color is out there, every color has a complementary color. If you have a complementary color, it'll be, if you add them together, it'll make white. We know things like if you add blue and yellow together, you get green, right? When two of the primary additive colors are combined, right? So if you add red and green, you get yellow. If you add red and blue, you get magenta. If you add blue and green, you get cyan. Why is all of that important? Well, those are pretty much the three colors of your color printers, right? Yellow, magenta, and cyan. They allow you to print pictures in color. And, or like me, it allows you to dry out and you have to replace the color tanks, but that's beside the point. If we add in a third color, we get white. So if we take yellow, which is a combination of red and green, and we add blue, we get white. If we have magenta, which is red and blue, and add green, we get white. If we have cyan and add red, we get white. So complementary colors are colors that are added together to make white light. Complementary colors are colors that are added together to make white light. Now, Mr. McKeever, am I going to have to memorize what makes what to white? No. But you do have to know what complementary colors are, right? Remember, we talked about complementary angles in math, are angles that make things right. Well, think of this way. Complementary colors here are things that make things white. Right and white rhyme. Oh, there are so many. Never mind, I'm just going to move on. When two colors are added together, they produce white light. They're called complementary of each other. Yellow and blue are complementary because yellow is the combination of red and green. Red, green, blue light all appear white. By similar reason, we see that magenta and green are complementary, as are cyan and red. So kind of this is what it looks like. So pigment that's red absorbs blue and green, reflects red, right? Green absorbs blue and red, reflects green, all that kind of fun stuff. Right? So when we get down there, it kind of reflects things back. And we know that red and green are what make up yellow, right? Green and blue are what make up cyan. Magenta is red and blue. But color itself is a physiological experience and is somewhat subjective. We've all seen those pictures. Is it a blue dress or is it a gold dress? Is this a red ball or is it a purple ball, right? Persons with color blindness don't see colors the same way most of us do, right? If you're red-green colorblind, you lose some of that experience. No one can really truly tell you what you're experiencing, right? We all know that a particular color is, this, right? We could agree this ball is green. But I can never know what you see in that color versus what I see. And there goes my thing. All right, time for my brain thing. So everyone experiences things a little bit differently. I have a friend who had a green Toyota Corolla, who this day argues with me that it wasn't green, it was blue. And I'm sorry, it was green. They say it was blue, I say it was green. We agreed to never speak of it again because we argued about it for a while. Dr. Lotto actually explained that we see things not as they are, but as they have been most useful for us in the past. This kind of explains why we develop towards a favorite color, because usually our favorite colors relate to something that was important to us in the past. Color is the quality of light that a particular surface reflects. My personal favorite color is purple. I really like purple. I don't know why I really like purple, but I really like purple. All of my LEDs in my office are purple. When I turn off my light in here, this whole office glows purple. That's one of my favorite colors. Your favorite color may be green. It just depends upon your personal preference. There's a lot of studies that have shown that maybe that's the color that we respond best to visually. And it gives us a sense of comfort, right? Which is why some people are triggered by something like a red color, right? When we talk about seeing red. So what may be useful to think at this point is we use color to make meaningful sense out of our world via vision. Once we realize that even color is perceptive, we start to understand neuroscience as a whole, because that means a lot of neuroscience is perception, maybe not necessarily reality, right? And you've always heard that term, perception. I don't know if you've heard it, but I've always used it. Perception is reality, meaning the way somebody perceives something is the reality, especially if you're dealing with somebody that's maybe got a psychological disorder, right? If they perceive that this Coke is their Coke and I tell them it's not, well, guess what? I just drank their Coke, even though it was mine. Perception can be reality for certain people, right? That's why if you get with people and you're arguing about that blue, green, gold dress, right? They're always going to see it their way because that's the way they perceive it. They can't see things your way. That's a really good kind of segue into the way we exist in politics today, isn't it? We have a really hard time seeing other people's way. And when we try to, especially if it, counters one of our own personal biases, it can be really hard to understand where that person's coming from. Just saying, it's not much different from physiological perception of color. So light emission. How do things emit light? Well, excitation is when electrons of a certain type of an atom, for example, oxygen or nitrogen, can only absorb a certain amount of discrete energy. Discrete always implies specificity. For example, if you try to ride the bus, but the bus fare is $1 and you only have $1, you don't have the discrete amount you need, so you're not going to get on the bus, right? So oxygen and nitrogen all have a specific amount they can absorb, and after that amount's absorbed, at that point, de-excitation is going to occur. And that's where an electron releases a discrete amount of that energy off as a photon, right? That photon of light is going to carry energy. Our lights all around us are exhibiting photons. We're exciting that whatever is inside the medium that's inside of them, and they're giving off photons. So sodium vapor street lights, yellow-orange, mercury vapor may be blue-white, right? That's why those old CFL bulbs are kind of a little bit dangerous, because the CFL bulbs inside of them had a mercury vapor. And always said if the glass gets damaged, quickly distribute or dispose of, and don't allow them to sit around. Flame on a gas stove burns blue. Space heater will light up orange red if you even turn on a heater, unlike me. Your stove itself, right? If you have one of those burners, they light up bright red because that's the way it gets reflected. Light emission is a result of excited atoms undergoing de-excitation, meaning they're giving off an excess amount of excitation so that they can release that energy off in the world. Because what would happen if they stayed excited like that? Well, science could say that those atoms would literally rip apart. So they know that they can't contain any more of that energy. So they give off photons to release some of that energy. And those photons are what we see as light. Well, certain creatures can do this thing called bioluminescence in certain actually areas. Bioluminescence can be the creation or emission of light, not by excitation, but by creation from bacteria, right? Some marine life can do it. Some insects, fireflies, right? Their little butts light up whatever color you can argue this. It's green, it's yellow, it's orange, it's green. They always light up green to me, but whatever, that's my perception of the light, right? Some animals reflect a certain spectrum of light, like a scorpion. I don't know if you ever know this, but if you put a scorpion under a UV light, it lights up kind of greenish and it makes them easier to find, which can be really useful in this area. They actually make specific scorpion lights that you can get to check your area for scorpions. So if you go out camping in this area, it's really important to get one of those lights because, man, those scorpions love to get in your tent, right? They come in looking for food. Because where you're at probably attracts bugs. Bugs are snacks for scorpions. And also they just like to cuddle. Scorpions just like to cuddle with you. I love this picture of this bioluminescence of this water up here, right? Because there's bacteria that's causing bioluminescence to occur. There are certain species of cave fauna that literally create light enough that human eyes can see with. And there's actually a lot of studies of deep sea creatures that create bioluminescence down there that shows that even deep sea creatures require light to function. So let's talk about the skies of blue, fields of green. Skies. Why is the sky blue? Well, because it's depressed. So the sky's naturally blue. No, that's not why the sky is blue. The sky is blue because component particles scatter specific frequencies of light and cause it to look that way. Right, the beam of light falls in the atom, causes the electron in the atom to move temporarily into larger orbits. Then it releases those photons, right, that readmission of light. They emit specific light waves, very tiny particles. So in the air, the nitrogen and oxygen molecules that are out there ring like tiny bells, right? They start getting excited by sunlight. And like the sounds from the bells, the light is sent off in all directions. That light that it gets sent off is typically a blue light. Right? So that ultraviolet again is absorbed by ozone. And so in the visible frequency, right, we get that kind of violet light scattered, followed by blue, green, yellow, and orange in that order. And so our eyes become more sensitive to that blue that we see. That's why we see the blue sky, right? At night, the angle at which the earth is striking the sun is striking the earth changes. And at that point, because that angle's changed, now those atoms are getting excited in a different way, and you may get red and orange or yellow skies at night, right? We had an old phrase back in where I'm from, right, is red sky at night is a farmer's delight. Red sky at morning, farmers take warning. Because there's some signs that show that if you do have a red sky in the morning, it typically is going to mean that there's a lot of moisture in the air and you may have storms coming. It's not hard science, but there are there's some correlations there, right? Our eyes themselves, when it comes to the sky, is more sensitive to blue because we see the yellow of the sun. That's why we see a blue sky. It's also why if we look out at the ocean kind of looks blue to us. Think about the ocean. The ocean's a lot of oxygen molecules there, right? H2O. Under different conditions, obviously, the sky changes. Where there are a lot of particles and require larger oxygen and nitrogen molecules, the lower frequency of the gas are scattered more. It makes the sky less blue. It takes on almost a whitish appearance. After a heavy rainstorm and the particles have been washed away from the sky becomes deeper blue. The higher that one goes into the atmosphere, the fewer molecules are there to scatter light, and so the sky starts becoming darker and darker until we end up in space, right? And in space, it looks black. In space, if you're on the moon, everything around you is going to look black because there's no atmosphere absorbing that light. So you kind of get this lack of reflection of light. So how do we perceive light as humans? Well, we perceive light as humans via the eye. Like everything about us, that eye is a remarkable device. The cornea is transparent, allowing light to pass through. Once inside, the light's manipulated in order that we might make the meaningful sense out of our world. In many respects, the human eye is much like a camera, right? Light enters through the transparent covering of the cornea. The amount of light that enters is regulated by the iris, which is the colored part of the eye that surrounds the pupil. Pupil is the opening eye, which light passes. And then it passes through it to the layer of tissue of the back of the eye, the retina, and then the retina will receive that and kind of change the way it looks. The retina itself is not uniform. There's a small region in the center of our field of view that we have the most distinct vision. The most distinct vision is called the fovea. The fovea is the focus area. Much greater detail can be seen here, right? That's why if you sit here and I'm staring at my screen right now, I have a really good vision of my screen. I have views all the way out here, but it's not as clear as where I'm looking directly. And I can change my fovea, right? If I move further away, it changes the focus. There's also a spot in our retina where the nerves carrying all the information leave in a narrow bundle. This is called the blind spot. So you do have a blind spot in your vision, right? We know about those blind spots for when we're driving. In both the camera and the eye, the image is actually upside down, right? It's compensated for both cases, right? In camera film, you just turn around and look at it. The brain has learned to turn around and flip the images so that we see things normally, right? Really, when I look at this here, right, the picture of my Pima logo, it's actually backwards and upside down in my brain. But my brain has developed over time to know that that would really mess up my perception of the world. So it flips it and inverts it for us. It's actually kind of interesting the way the brain works. Principal difference between the camera and human eye has to do with focusing. In camera, focusing is accomplished by alternating the distance between the lens and the film or the chip. In the human eye, most of the focusing is done by the cornea, the transparent membrane of the outer eye. The image gets focused on the retina by changing the thickness and shape of the lens to regulate its focal length. This is called accommodation, and it's brought about by the action of the ciliary muscles, right, which surround the lens. It allows the eye to kind of change shape and form. You're able to focus and look a little differently, right? Have you ever done that where you're trying to read something, and you're looking at it, it's really tiny, and you're like, you focus really hard, and all of a sudden you can read it. What's happening is your ciliary muscles are working to kind of focus it. So in the eye, we have a couple important parts. We have the cornea, which is the process of beginning to bend and focus the light. We have the pupil, which is much like you because you're a focused light, right? It's a muscular ring that can change the size to allow more or less light in depending upon the factors, right? In available or ambient light, the pupil is going to change. Oh, my camera, my phone here, right? So my phone, if I can get close here that you can see, my eye currently has a certain size. If I take my phone and I shine a light in it, my pupil is going to change size, right? Because it's going to adjust for the amount of ambient light in the area. It can also change because of your emotional state. If you're ever seen anybody that's really, really, really peeved off, their pupils are really tiny and constricted. That's how you can tell if your spouse is really getting angry at you. Guys, warning, you start seeing your significant others, oh, not guys, everyone. Just say guys, because we're usually oblivious to it. When those people start becoming pinpricks and focused, that means the emotional state has gotten out of control at that point. It's probably time to back off a little bit. I'm just saying, right? Chemical changes can cause your pupils to change, right? Different drugs. I was on for a while Neurontin. Neurontin is a drug that helps with the nerve problem that I have in my arm, the neuropathy. The problem with that is it allowed my pupil to not change effectively. So it was really affecting the way I viewed things, and it was affecting my vision. I had to get off it because it really caused bad effects on my vision. So once we get past the pupil, then we have the lens, which continues to fine tune the light. We have the vitreous humor, which is not very funny. It's the gel-like substance in the center of the eye. So if you lose your vitreous humor, you're not going to have a funny day. Just saying, right? Vitreous meaning fluid-like. Then you have the retina, which encodes the light into something we can use. We have rods and cones in our eyes. The rods allow us to see in black and white. The cones allow us to see colors. And if you're ever having a problem remembering that, cones starts with C, color starts with C. Cones allow us to see color, rods allow us to see black and white. And then the brain itself is then going to decode our image, right? So literally what we're seeing is being transmitted into our brain in an electrochemical signal, and the brain is making sense out of it. It's actually just, I mean, it's fascinating when you look at that. With normal vision, your eye can accommodate to clearly see objects from infinity, a far point away, down to 25 centimeters, the near point of your face. Unfortunately, most of us don't have normal vision, right? We have people that are farsighted or hyper excessive opia. The person has trouble focusing on objects that are nearby, but sees things further away. When a person is farsighted, their eyeball's a little too short, and image focuses behind the retina. Farsighted people must hold things more than 25 centimeters away in order to focus them, right? Do you ever see an old person do one of these? Or Mr. Keeper doing one of those, right? The remedy is to increase the converging effect of the eye by wearing lenses or contacts with converging lenses. Converging lenses converge the rays sufficiently to focus them on the retina instead of behind the retina, right? So a converging lens is going to be used for somebody that's got farsightedness. The other object is a nearsighted person. A nearsighted person can see objects nearby, but not distantly too far away, right? The distant object focuses too close to the lens and it forms in front of the retina. The eyeball at that point is too long. At that point, the best option is to wear divergent lenses, which diverge the light away so that it focuses on the retina instead of in front of it. So a nearsighted person wears divergent lenses. You can also get a term called astigmatism. Astigmatism is an effect that results when the cornea is more curved in one direction than the other. And this can really make it difficult to get contacts. You used to not be able to get contacts for astigmatism because you couldn't make contacts specific to the shape of the eye. Because of this defect, the eye doesn't form as sharp of image, right? The remedy here is a cylindrical corrective lens that have more curvature in one direction than another. Then you got some glaucoma, right? Glaucoma is caused by diseases that are responsible for optic nerve damage and eventual vision loss. Glaucoma has to do with the pressure in your eyes. And every single person in Nevada used to want to have glaucoma because glaucoma, because of the problems and pressure it puts on your eyes, could qualify you for medical cannabis. Now we don't have to worry about that, right? Cataracts, right? Cataracts is the clouding of the lens. It's not a car made by GM. Cataracts is the clouding of the lens of the eyes, leading to decreased overall vision. This is where kind of you get a fuzziness over the eye. Unfortunately, a lot of times you start getting a cataract that's permanent. There's no way to really fix that. There are some surgeries out there that may improve it, but it never really fully goes away. Amblyopia, I love that term, is the loss or lack of development of central vision in one eye that's unrelated to any eye health problem. It's not correctable with lenses, right? You can also get diabetic retinopathy. It's a person with diabetes causes progressive damage to the retina and light sensitive lining in the back of the eye. Literally, they start having sugar crystals in their blood vessels in the back of the eye, and it can damage their eye. Presbyopia is something none of us can escape. It's age-related visual breakdown, right? Over time, all of us will lose some of our sight. Just like everything else in our body, our eyes are designed to break down, and you get presbyotic vision changes. So eventually, there's a good chance that most of you will need corrective lenses by the time you get late into your age. So how can we use light in physical therapy? Well, that's a great question, Mr. McKeever. Why don't you talk about that? Well, in infrared, we can use it in medicine to help locate areas of increased body temperature. We can use an infrared detector, and it can show things. Not only does it show ghosts in those ghost shows, but we can find areas of increased body temperature, which may be indicative of inflammation, right? If we look at this person here, right, they've got some increased light or some increased heat down around their sacrum, which is normal. We have some increased heat up towards the upper body, which probably is they're working out. But if you look in that right arm, man, they've got a ton of inflammation out there on the aspect of their arm. And that kind of tells you we've got an area of localized inflammation. We've also got some areas of localized inflammation, which is really weird to me. We've got some areas down here too, which I don't want to know. But that tells us where we have localized inflammation. We can also tell us that that upper back area of their back is, especially if they haven't done anything, is really kind of inflamed and may be indicative of problems. They may need to have something to help that. We can use UV. So we use the lower spectrum. Now we can use the upper spectrum, ultraviolet. We can use this to treat chronic skin conditions such as psoriasis. My main area I've seen it used is wound care, right? It has really shown promises in killing antibiotic-resistant bacteria such as MRSA. It's also used to treat water. You also use UV to tan your skin, right? But there's a new machine out there that's fantastic for hospitals. It's this little robot that they can program to go in different rooms when there's nobody in there, right? You send it in, close the door, and it sends out a mass dosage of UV light in that room. And that UV light kind of bounces everywhere. You got to remember how light works. It bounces off of everything. And as that light's bouncing around the room, it's finding these antibiotic-resistant bacteria and the viruses, and it's killing them. So they can use these little robots with this bright UV strobe to bounce it off every surface in the room and can actually get a really, really good, thorough cleaning of the room before a new patient comes into the room. Can kill things like MRSA, which is really, really hard to kill. It's fascinating technology. They now make those UV cleansers for your phone that you can put your phone in, close the lid, and it bombards your phone with UV light, and it tries to kill the surface. Your phone is a really, really dirty surface, just to let you know. Not quite as dirty as your toothbrush, but pretty bad. Speaking of toothbrush, my toothbrush has a UV chamber in it that I can take the head off my toothbrush, put it in, close it, and I can UV sanitize my toothbrush, to kill all that fecal coliform that's floating around in my bathroom. Everyone has fecal coliform in their bathroom. We'll talk about that in patho. But UV light is actually really interesting for use in wound care. If we've got an infected wound, we can use a small dose of UV over it and help kill all that infection that's now raging inside that wound. Because we know that we can't start healing that wound until we've gotten rid of the infection. Again, it's used to treat water. A lot of you probably, if you look at the way your water comes in, probably has a UV treatment on it. It's been sold quite a bit lately because it does kill a lot of bacteria in water. We can use shortwave diathermy. Now, diathermy uses more radio waves than it does light, but there is a microelectromagnetic wave that we use on light as well. It's used to heat up tissue. So this is a picture of a diathermy machine here. The neat part about diathermy machine is we don't have to have the patient's skin exposed for it. We're going to talk about laser in a second where we do, or ultrasound where we have to have the skin. With diathermy, we just put the applicator over the area and it'll send those radio waves in and heat up the tissue. And it actually heats it up pretty deep. The downside to it is this is a small diathermy machine that you see here. Most diathermy machines are like big honking, room filling machines. And that's why we kind of got away from using them. They're actually really great machines. And if you go to places like nursing homes, skilled nursing facilities, transitional care units, they tend to use diathermy a lot. And mainly because they bought the unit, so they're going to use it, right? It's really good at kind of warming up tissue. A lot of the older folk really like it when they have, conditions where they need tissues kind of loosened up. Maybe they've got frozen shoulder. Diathermy can really kind of loosen it up. It's not going to totally relieve it, but it can be really effective at warming that localized tissue up. Downside to that is it's, again, radio waves. So whatever. Laser, pew, pew. Light amplification by stimulated emission of radiation. So laser, again, is radiation. We can use laser in surgery to target specific tissues, right? The YAG laser can be used to destroy floaters and shape tissue and accumulation off the eyes, right? I'm sure that some of you guys have had maybe LASIK surgery, where they go in and focus a laser beam on your eye to try to improve the overall vision quality of your eye. I wish I could get LASIK. I actually really wish I could. Even if it would improve my vision just a little bit, I'd really like it. But my eyes aren't quality or aren't candidates for laser. There's also stuff like gamma knife and all kinds of lasers like that emit gamma beams, and they're used to treat cancer. They're used to go in and literally burn off cancer cells and kill off cancer cells, which is really kind of cool. Again, I told you, I geek out about physics. This stuff is just awesome to me, the stuff that we can do. But in physical therapy and in chiropractic settings, I have to add them too, and sometimes in massage, we have a new term called, or a new device called a low-level laser therapy or low-light laser therapy. And what those devices do is they use a specific wavelength, right? And it depends upon the gas that's inside the laser, what wavelength it'll occur. that's actually able to penetrate all the way down to almost the bone level. You'll find that when we talk about most modalities only go about 5 centimeters deep into the body, right? Not a very big depth. Lasers have been shown to go pretty darn deep. And, in the clinics I've worked with laser, I've had really, really good results. Now, if you get a laser treatment, most of the time you don't feel anything. So that's why patients don't like it, because you're like, well, I came in, I got my laser treatment, I don't feel any different. And there's actually a clinic in town here that does cash pay laser business. So literally, patient gets an eval from a PT, and the patient may come in 3 times a week to get laser, and they just pay cash pay for it. Because it takes 3 minutes to get a standard laser treatment. It's actually pretty cool. I really am a huge fan of laser. The problem is there's not a lot of research out there on how it's effective and the efficacy of it and stuff like that. So we're still working on that. So a lot of insurances don't reimburse for it, which is why if you're getting laser, most times it's a cash pay basis, right? But I always tell my patients, just like we mentioned in a previous lecture, laser works at the cellular level. Laser is going to get down there and excite those mighty mitochondria. And when they get excited, they bring in more localized blood flow. More localized blood flow brings in more nutrients brings in healing, right? Similar, we'll talk about with ultrasound, works very similar. It's just ultrasound doesn't penetrate as deep. I had a really just tremendous effect on trigger point release with this laser, where I had patients that had chronic trigger points we couldn't get rid of no matter what we did. And we'd hit it with a class laser and boom, trigger point gone. I had one patient I remember specifically, quarterback for one of the local schools, who had just the nastiest trigger point ever in his rhomboids. And we did everything. Man, I dug at that kid's back for hours some days. Could not get that trigger point to release. So I said to the PT, hey, can we try laser for it? What the heck? We tried everything else. Tried ultrasound, we tried diathermy. Let's just try laser. And, I'd read about the NFL now starting to use laser in treating their athletes. And sure enough, we used it 2 visits and that trigger point was gone. Like that, magic. Now, I can't say that the laser was a specific thing that did it because, again, I didn't have a good controlled study and stuff like that. But man, it was just gone. He had no more trigger point. Came back in 2 treatments later. So I don't know what you did with that laser, but it's gone. And we could not locate it by palpation. It's pretty neat. So lasers are an up and coming technology. And there are about 5 clinics I know in town that use LLT for treatment. Mirror box therapy. This is a neat therapy. We've discovered that using a mirror is useful in treating patients with pathologies like chronic pain, phantom limb syndrome, RSD or CRPS. The mirror can be used to trick the brain into seeing the affected body part as if it's working normally. So if I have CRPS in my right hand, I can block off my right hand so I can't see it, have a mirror reflecting my left hand and have me doing left hand motions. And for whatever reason, the brain thinks it's my right hand that's moving. Right? It tricks the brain into seeing the affected body part as if it's working normally, right? And we can use that to decrease pain and stuff like that. It's really effective in patients that maybe have amputations. I've had patients that are talking about, oh my God, my hand hurts, and they have no hand. So we'll put that limb in the box. We'll get their other hand out here and we'll have them, okay, open and close that hand. And they're looking at that box and like, oh my God, this is so much better. Or I've had a patient once that had a horrible itch in their right hand and they had no right hand. So we had him put the arm in the mirror box. We had the other hand here and we scratched his palm. And it was just fantastic. And he's like, oh, it feels so good, right? He was finally able to trick his brain into scratching the hand that wasn't there. It's pretty neat the way that works. I mean, it's just the treatment of phantom limb and RSD is just amazing with mirror box therapy. It has to do with the way the brain perceives the environment, but it's just really neat that we can do that. All right, so there's your assessment questions. I'm going to stop sharing now. So that is going to conclude the lecture on light. I hope you found it a light subject, not a heavy subject. Snecky has moved. Snecky's now over my head if you haven't looked for him. I'm going to keep moving him around the room, see if you can find him now. Grumpy Cat's decorated for Christmas back there. If you have any questions, please reach out to me. If there are no other questions, hopefully we'll see. I think I can actually see you physically on Monday, or not physically, but virtually on Monday, I'm hoping. Otherwise, reach out to me if you have any questions. I reposted my open lab hours or my open office hours. Again, I have Tuesday evening open hours. I also have Friday afternoon, early afternoon open hours. If anyone, for any class, please, for any class at all, if you are having problems, please reach out to me. I don't care who you are, what your problem is, what the class is. Reach out to me. I want to make sure you guys are getting the most out of this, and I don't want you guys being frustrated. I make no judgment. If you're like, I can't remember the ABCs, well, let's get together and we'll sing the ABC song together. Okay. But again, I'm going to re-stress what I have over my shoulder over here. Please think before you gather for the holidays. The last thing you guys need to do is go to the ICU in your first semester. Okay. So please think. This holiday season, skip out on those gatherings. If we skip this season, we'll be there for next season. Think about that with your grandparents, with your parents, stuff like that. If we just skip this season, they'll be alive next season to spend with us, hopefully. If we don't skip it, there's a good chance they may not be. I just want to stress it because I just read about a whole campus that had, not our campus, not our school, but another school that it was some sort of medical program. I don't remember what it was, but they held a potluck and all got together. And they ended up infecting something like 37 other family members with COVID because one came in with COVID, spread it to the rest of the people. Some of those people got sick, but also they spread it to mainly their family members that are compromised. So think about that, folks. Traveling. I know the CDC says planes are fairly safe because they do circulate and sanitize the air as it goes through the plane, but you have to go through the airport to get on the plane. And I don't know if you guys have seen the airports lately, but the airports are freaking nuts. And no one is obeying the rules and the safety rules in those airports. They're snotting everything up. About a month or a half ago, I took a trip and I quarantined myself afterwards, right? It was actually more than a month and a half ago. It was probably 3 months ago, now that I think about it. But, like I told Southwest about 2 people that I was worried about getting on the plane because they're sitting there hacking up their lungs and they're sweating profusely. I'm like, I'm not getting on a plane with them. They've got bad stuff, right? Think about this before you do things, guys. Okay, I know I'm recording this and I wanted to make sure it got out to you guys, but I want to see you guys graduate on time. Think about it this way. If something happens where you guys miss a significant portion of your class and you're not able to make it up, you have to then step out of the program and come back with the next cohort when they come back. So maybe you make it through first semester, but you're beginning a second semester, you're out because you got COVID. You've got to wait until cohort 13 hits second semester before you can re-enter the program. That's the way the reentry program works here. There's no way we could do you a special second semester. So that means, the current cohort for you guys, right? Cohort 11 graduates in June, I think, something like that. March, maybe, I don't know, somewhere around that range, right when you guys are at the end of second semester, they graduate. That would mean that cohort 13 would start then. They'd have their first semester, and you'd be looking at late next year, early 2022 before you can get back in the program. Don't do that. Don't sell yourself short like that, right? I know family members. I know I want to gather. I don't want to be with my friends, but that's beside the point because I'm kind of an introvert. But I know that need for human interaction is there. Hold Zoom sessions like this. Have a virtual cocktail hour. Have a virtual Coke hour. I don't know what to tell you. I'm just trying to say, please protect yourself. Don't put yourself in a situation where you could get COVID. We're so close to having the vaccines, guys. We're so close. And I will tell you right off the bat, I had a couple of you actually email me about this. I will be the first in line, rolling my sleeve up. Hit me up, guys. I'll be the first one in line after I read some of these reports on this. There's some things in it that, obviously with all vaccines, you're going to get a little bit of a fever. You're going to get this and you're going to get that. Yeah, sure. Give it to me. Yeah, it feels good. Give it to me, baby. Right? I want those vaccines. I want to show you guys that it is, and actually all the faculty's that way at this point. We're all kind of going, okay, we're going to sign up. We'll be the first people to get it to show you guys that it's safe. Anthony Fauci, same thing. Dr. Anthony Fauci, well-respected man said he'll sign up to be the first people to broadcast for it. I will stream it if it will make you guys feel better about getting the vaccine. I will stream me getting that injection. But until then, protect yourself, protect your family, keep yourselves distance, keep yourself safe, mask up, double mask if you need to. I double mask now when I go to the grocery store or when I go out to get my mail, because my mail is at a UPS store. I double mask. I sanitize getting out of my truck before I go into the store. And as soon as I hit my truck, because I put all my stuff in one bag and I have carry-all bags for all my mail, it all goes in there, sanitize as soon as I get out. And when I get home, all my boxes get sprayed down with Lysol before I open them up. I'm really paranoid about this now, guys. I don't want to get this again. That was terrifying. Okay. So please be safe. I know that was a little addition onto this that has nothing to do with physics, but I want the best for all of you. I hope you realize that. If you're having any problems with anything, please reach out. Even if it's just you need a psychological kind of booster. Mr. McKeever, can I sit down and talk? I'm having a hard time with COVID in my family. Call me. One of my degrees is in psychology. I'm not going to be your counselor. Please don't think that. That's not what I'm saying. Excuse me. Oh my God, COVID. No, just kidding. But I will listen to you guys and I will sit down and I'll talk to you guys. So I'm here for you. Reach out. Other than that, have a good weekend. I hope to see you all soon. My weekend plan is to get some good gaming in this weekend. That I need to step away from working so much and actually get into some good gaming. I think it might be a little bit of Warzone weekend for me this weekend, maybe. So I will catch you all later. Have yourselves a great afternoon and doses.